Dmitry Maslov from Edge Impulse. And Dmitry's going to talk about leveraging generative AI for visual anomaly detection. So really interesting sort of mashup of transformer-based models with what would be traditional, more CNN-based models. So, hello. Fantastic. Dmitry, welcome.
Good morning, everyone. 大家早上好。我会讲中文, but my presentation is going to be in English. So my name is Dmitry Maslov, and I'm a senior embedded engineer at Edge Impulse. I think there's plenty of people here in this room that are familiar with our platform. We have lots of things going on at Edge Impulse. But today, my talk is going to be about visual anomaly detection on MCUs with generative AI. And because, as you see, my title is an embedded engineer, so I decided to structure my talk in a very engineer-wise structured way. So my talk is going to be chopped up into three pieces. The first one, we're going to be talking about the anomaly detection and visual anomaly detection specifically. What is it and how it is important? Then we're going to be talking about the MCU part, like how to optimize the algorithm so they can be run on the smaller devices. And then finally, we're going to talk about how to sprinkle a little bit of that secret generative AI sauce on top. The first part, visual anomaly detection. Right? So that fun picture there, it's representing that the neural networks, the big ones and even the very small ones, they don't know when they fail, and they can fail very hard in some cases. I mentioned this dichotomy between tiny and big ones because we know with language models, large language models, there is an issue of hallucinations, right? So the language models tend to hallucinate, but I would say that the problem is even more serious with the very small models, because the small models that we run on the edge devices, they only have that much footprint, which we can, compress all the information into. So there is more potential for failure when encountering the situations that the model they are not in the training data, right? And so that fun example with Chihuahua and muffins. Like imagine you're a machine learning engineer and you're training the model to recognize cats and dogs. Okay, that's all very cool. So your model is going to look at the muffin and it's going to be like, okay, I see some eyes here and that looks like a skin, so legit, it's a dog. Okay, problem solved. Which is, of course, okay, that's not true. You can be smart machine learning engineer and probably will be, so you're going to add something like unknown or background class. But the thing is, so when you develop your machine learning model, you'll be like, okay, so I have cats, dogs, what else? Table, a sofa, but will you put muffins in your data set? Nah, maybe yes, maybe no. That's the problem. Like here, when talking, I think, a speaker from like a few presentations before from ST mentioned the field testing is actually a huge part of the Edge AI development process, because you get out of the lab and you realize your model just encounters all sorts of weird stuff in the real world, right? And it's very difficult to predict everything that the model will encounter in the real world. So the solution here is anomaly detection, right? And it's not super new thing. Like here you see the interface for k-means clustering, anomaly detection. It's been around for a while. K-means is very simple, very powerful. Basically what we do is that there is a separate anomaly detection system that is for flagging and managing the anomalies. Basically, we only trust the outputs of the models when the data falls within expected distribution. So we have the training data, which represents our normal data, and then we have some data points that do not look like anything that we encountered before. Okay, so this is anomaly. With k-means, it's very simple. It's easy to visualize, right? I would say that, as I mentioned, this is actually very tried and tested for non-visual data. When you go around exhibitions, and you probably will see something like a fan anomaly detection demo, maybe a pump, something like that. So it works with vibrations, perhaps. So at Edge Impulse, our CTO is Yangon Boom, and this was one of his main, basically, observations. You go to a place like Embedded World, and they are all the companies that they show computer vision demos, but they don't run visual anomaly detection. So it's very easy to, just put something that the model does not expect, and yeah, the output is wrong. So now moving on to specifically visual anomaly detection, which is much more interesting. So at Edge Impulse, we actually have two ways of doing that. We developed that. First one is Gaussian mixture models, and second one is the patch core. So Gaussian mixture models is actually a more generic way of so it's also a clustering algorithm, very similar to k-means in some cases, but it works better for certain reasons because, okay, actually, next slide because I have a picture here. A better way to understand Gaussian mixture models is perhaps to compare it with k-means. K-means is a centroid-based algorithm that partitions the data into clusters by minimizing the sum of square distances between data points and the assigned centers of the clusters. And in contrast to that, GMM, or Gaussian mixture models, is a probabilistic model that represents each cluster as Gaussian distribution and models the data as mixture of these distributions, Gaussian distributions. So when we process the data, also similar to k-means, GMM calculates the likelihood the data belongs to one of those probability distributions. And if it doesn't quite fit, then, like if it has a very low probability of being generated by the mixture model, it's flagged as an anomaly. So this way it works for regular, for example, time series data, and also with a few very simple additions, like random projections and then average pooling. So basically, like we start with the feature extractor, which can be, in this case, for example, mobile net, and then we apply a random projection, average pooling, and like at the end we have a set of features which can be clustered by Gaussian mixture model. And Gaussian mixture model, so they're a bit more powerful in this case than k-means, and also the clusters, they don't have to be spherical, they can be elliptical. Okay, no, the other way. Oh, okay, that button. Yeah, and the patch core. Patch core is actually a very recent addition to our collection. Basically, like we launched it a few months ago. Patch core is specifically algorithm for visual anomaly detection, and it focuses on small image regions or patches rather than entire image. It first learns, so during the training phase, how normal image parts look like by studying parts of the normal image. Yeah, here is the screenshot from the research paper. And then a core set, so a compact summary of the normal patches is created. So there is, you see the core set. Actually, I mean, like if starting from the beginning, so we start also with the pre-trained encoder, which can be a mobile net or efficient net, depending on how granular you want the features to be. So later at the inference time, which is here, basically we compare the patches with the core set, and the sample is classified as anomaly if at least one patch is anomalous. And then we also provide the scoring of the different parts of the image. So patch core and GMM. Here you can see some examples actually how it looks on our platform, and this is an example of the GMM anomaly detection. It's a concrete cracks data set. GMM in our experience works very well in the cases like this one where anomalies are relatively large and more or less easily to spot. And you see the grid here is pretty coarse, right? Over there, you see an example. It's our own curated data set. So it's basically DHT11 sensors, maybe you know them. And that one is quite fun because I remember I looked at it on Slack and our product manager was like, oh no, it misclassified it. It looks pretty normal to me. Like if you look very close there, so that DHT11 is blown up, right? So yeah, it's probably was damaged in the process of usage. And it can still pick it up very well right here. So, and you see, with the patch core, we use higher resolution, and we can detect much more granular, much smaller features. So like this is how it looks in practice in Studio. Okay, and the next part is on MCUs, right? It's all really great, but if you can only run it on something like a Jetson O-ring and Nex, yeah, it's not that great. We want to be able to run it on really small devices. So we have a couple of tricks in our sleeve with Edge Impulse. There is an Eon compiler, which is basically, it's a really an umbrella term we use because it's more than one single technology, but essentially it compiles the machine learning models into highly efficient and hardware optimized C++ code. Basically, we just throw away all the stuff that is not really necessary to run the model, strip it down, and we can reduce the RAM usage by 25 to 65%, and then ROM usage by 10 to 35%. And it has the same accuracy and also same latency as the TF Lite. Now, there is additional optimizations applied. There is a RAM-optimized version of Eon compiler, and there's slightly longer explanation, but I'm actually the person who works in Core SDK, so I kind of know most of this particular stuff. This is just basically patch-based inference. I mean, maybe some of you who work with like ML, that you know that the convolutional networks, there is an easy trick to save up some RAM, is if you just take parts of the image and first calculate part of the feature map and then move on to the next one. You don't need as much RAM as you normally would if processing the whole feature map. All right, and of course there's quantization applied, both to the weights and activations, which just basically transforms the weights from float 32 to integer 8s. There's a couple of more optimizations. Yeah, so here are the graphs, and the comparison here is between TF Lite Micro, Eon compiler, and Eon compiler RAM optimized. For the RAM optimized, you can see that we can achieve, the larger the model is, the more RAM savings you can get. And otherwise, yeah, so for smaller models, it's not that significant. For larger model, it is very significant. As you can see, it's basically half of the TF Lite Micro. Right, and this is for ROM usage, so flash savings here. Basically, also compared to TF Lite Micro, we are able to achieve some pretty good savings on the flash side, again, by stripping down what is unnecessary from the inferencing engine. Yep, so this is a video. No? Okay, wait. How am I going to do that? Is there like... Okay, perfect, thank you. Yeah, that's me in my office, and I'm running the GMM Gaussian mixture model. Well, this is my debugger over there. Rubber duck debugging, okay. Yeah, so basically the model itself is trained on just an image of the desk, and then it recognizes everything else that is not the desk as an anomaly. It's a very simplified example. What I wanted to show is just, it's running on ASP32, and it's 400 milliseconds per inference. So if you know, ASP32 is pretty old microcontroller. Like it does not by itself have any SIMD vector extensions. So yeah, it's works on ASP32 as well, but I have some more metrics here. So Aleph Ensemble, we are also running out on Aleph Ensemble board, and it's super fast there. It's 4.3 milliseconds for FOMO AD, FOMO AD GMM, Visual AD GMM, and then Raspberry Pi is 3 milliseconds estimated, and Cortex M7 28 milliseconds. So it's all very fast. Here, the metrics are for GMM version specifically. The patch core, we're still optimizing it because that one is slightly larger, although we do plan to fit it on smaller MCUs as well. Currently, the patch core runs on Raspberry Pi. Okay, and as I promised, we're going to be talking a little bit about the secret generative AI sauce here. Basically, the language models were mentioned today, but at Edge Impulse, currently we believe, at least at this point, the age of generative AI on the microcontrollers and by extensions like also very small MPUs, it's not yet there. I think it's coming. It was already mentioned today, but it's not yet there. So how we apply generative AI is for the data curation, data collection, and everything that you have everything to help you to create that model that you want to run on the edge. So yeah, if applying it to visual anomaly detection, we have another problem, right? So, okay, so we trained the visual anomaly detection model, but we have an issue of testing it. It all comes back to the data, right? Usually, you have a lot of the regular, normal data because, well, you know where your device is going to be operating. You kind of know that. What you don't know is the things that you don't know, the anomalies. And here, the generative AI can help in two ways. So first of all, it can help you to automate the labeling process. This works really well. I'll show you in a moment in the screenshots. And it can also help you with the synthetic data generation, although for that one, there are some still caveats that apply. Yeah, so for labeling the unsorted data, when you have an actual system running in production, then, well, you can get a lot of data, and labeling the data is very labor-intensive. We just launched, like literally just launched, or in the process of launching, the AI actions and Edge Impulse, and basically that allows you to use one of the foundational models. Yeah, it can be one of the OpenAI models, it could be a vision transformer, but in this case, I was applying one of the vision-capable ChatGPT models to the same DHT11 dataset, and I just, on the next slide, there is more complete screenshot. Basically, you see that there is a prompt there, is the DHT11 sensor in the picture in good condition? Respond only with anomaly, no anomaly, unsure. And it worked really well. So that thing is really working without too much hassle. As you can see there's no anomaly, and here the legs are obviously missing, so that's an anomaly. And here we have a very blurry image, and I think it's also the DHT11 there is blown up, so it's an anomaly as well. So that can help you to label the large amounts of data. And finally, the last piece is that you can also generate synthetic data in Edge Impulse Studio with DALL-E, Flux, or RealWiz, or you could even use NVIDIA Omniverse. Although in that case, I think the caveat here, because I also tried that, we have the capabilities, you can generate the anomaly data pretty easily. But with those image generation models, it will be pretty hard for you without additional fine-tuning, like with LoRa or something, to generate the normal data, which is still okay because, as I said, the anomaly data is the hardest to obtain. All right, well, thank you very much. Yeah, that was the end of my talk.